Okay, so we're looking at section 14.7, which is optimization. For functions of several variables. We'll start with two variables. There's some neat tools for two variables that don't work with more than two. Just the math gets more and more complicated as you add variables. Just kind of make sure we understand a couple of things here. This is a local max. Maybe this is an absolute max here. Now this other point, I've got this sort of an interesting thing that's between them. Whenever you have two maxes that are near each other, you can get one of these points here, which is, this is called a saddle. And saddles will arise when you're looking for maxes and mins. Saddles will arise because they have the surface at a saddle is just perfectly horizontal. Same as at the maxes and mins. So let me put in one more picture here for a min, obviously. Right down here is a local min, could be absolute. Okay, but at, we're just right now we're gonna do local extrema, which are local max, local min, or saddle locations. Okay, at each of these points, the directional derivative is 0 in every direction. Okay, so at each of these, both partial derivatives are 0. Which is another way of saying that the tangent planes are horizontal. Okay, so let me just go ahead and give a process. So given z equals some function in x and y, first thing you need to do is solve the system fx at xy equals 0, fy at xy equals 0. If the system is nonlinear, meaning that it's not, they are not linear functions, so nonlinear would be like it's got quadratic parts or sines or cosines or something like that. So if the system is nonlinear, find all solutions. If it's linear, then generally you'll just have one solution. There are exceptions, sometimes there's none. in a weird case or two, sometimes you'll find infinitely many solutions. Okay, so we would say solution points are called critical points. Okay. Then we have to test each critical point to see if it's a local max or a local min or a saddle. So step 2, for each critical point, you have to run the second partials test. You remember the second derivative test, right? This one's the second partials test, which I will not prove today, but I may prove next time. Okay, so here it comes. Let D be fxx fyy minus fxy squared. Okay. If xy is a critical point, and a d at x, y is greater than 0, and fxx is less than 0, then I should say at xy. So let me just make that a little more space there. Fxx at xy, the critical point, is less than 0. Now you just think of that as a second derivative. That's concave down if the second partial is negative. If it's concave down, then it's going to be a max. So f has a local max. At this critical point, xy. Okay. Why this is true depends on the direction. You have to learn to compute something called a second directional derivative to prove this. And this d thing that you're looking at is related to the second directional derivative. And basically, a second directional derivative, if it's negative, it's concave down in every direction. If it's positive, it's concave up in every direction. So we're thinking about this directional derivative in every direction. And from the directional derivative, you get this d thing. So it's related to the second directional derivative, but it's not the second directional derivative. I'll talk to you about this later. B, d of xy greater than 0, and fxx at xy greater than 0 means it's concave up. Concave up means a min. So then f has a local min at xy. Okay, C, d less than 0 is the interesting case. Implies that f has a saddle point at xy. Finally, D, if d at xy is equal to 0, the test yields no conclusion. So the test is inconclusive, which is another way of saying no conclusion can be drawn. The test has failed. We've got nothing for all that work we did. It's tragic. Now I'm going to dig up an example real quick here from my notes. I always like sort of hard examples, especially ones that mix the x's and the y's together into terms. So I'm looking for my hardest example. I've only got 2 examples here. I wrote SAD, S-A-D-D-E, and that should be saddle. Fixed it. Better. Okay, so that's the test. So let's go ahead and do an example problem. This one is pretty tidy. Let's see what happens here. So here I've got f of xy equals x squared. And here's the term where the x and y's mix. You get an xy, so I always like it when they mix like that. Plus a y square, plus a y. That's it. We want to find the local maxes, local mins, and maybe saddles. So we say find and classify local extrema. Okay, so we have to take both partial derivatives and set them equal to 0. So fx is 2x plus y, I think. Set that equal to 0. Fy is x plus 2y plus 1. Like that. Set that equal to 0. Method of substitution might be easiest. So from the first equation, you get y is negative 2x. Good. And then maybe plug that into the second equation. So you have x plus 2y, which is negative 2x, plus 1 equals 0. So I think that says negative, this is x minus 4x is negative 3x. Plus 1 equals 0, so I think x is a third. And over here, y is negative 2x, so that's negative 2/3. There's your critical point. Okay, so it's 1/3, comma, negative 2/3. Okay, I'm going to pause for questions. Fxy quantity squared. I think you're referring to this expression here. Yes, that's what that means. Fxy quantity squared. Absolutely right. Daniela is the second exam on the 15th. What's the date now? It's the 6th. Boy, it seems awfully close, but we have covered a lot of material. I'm not going to change the date on that, but we'll talk about it on Wednesday, because it would be a week from Wednesday. I'd like to finish this chapter. I don't think that's impossible. So, Daniela, I'd like to get this material done, and then the next exam would be chapter 14 on the 15th as scheduled. Okay, let's keep going. All right, so I got my critical point. The next part is to classify it. So we need to take these second partials. So fxx is going to be just 2. And fyy is also 2. And fxy, this is the partial with respect to y of fx, just to make sure you understand. So that would be, where is it? 1. Okay, then d is fxx fyy minus fxy squared. These are all constants, which is actually super nice. So this is 2 times 2 minus 1 squared. So that's going to be 3, right? That's greater than 0. Got it. Any questions? And then remember fxx is 2, so this is greater than 0. So when they're both positive, and that means it's concave, if it's positive, it's concave up. So the rule is d greater than 0 and fxx greater than 0. Local max or local min? If fxx is positive, it's concave up. Min or max?
Min.
Correct. This is a local min at the point 1/3 negative 2/3. Okay. All right, any questions about that? Let's see. I think I want to try and be brave here. Let's do this in Desmos. Not Desmos, we're going to do it in GeoGebra. So we want to pop over and do GeoGebra. The 3D website. Here it is. All right, and then I'm just gonna start typing this thing in. So you don't need to put in z equals, just put in x squared plus xy plus y squared plus y. Okay, so there it is. And I think you can see that min that we found. Okay. So let me see if I can pull this around so the x-axis, I don't know which one's x. So I think that's correct. So x is 1/3. Okay. Is that better? And y is negative 2/3. That works. So I'm just going to capture this real quick so I can put it in the notes. Okay, I'm going to put that back in here. I don't think there's room for it there unless I make it really small, and I don't know if I want to do that. So I'll move it down. All right, so let's just make sure we note here that the min is right here. So, and x was, what did we say, a third? So that's 1/3 for x and negative 2/3 for y, where the local min exists. Okay, so I'm just going to zoom out on that, wait for questions. If you have any, pipe up and let's hear them. Oops. Let me fix that a little bit. It's got a point there. Any questions about that one? E15. I want to do the absolute max and absolute min real quick, and then if I get a second, I'll do another example of those. Okay, so I'm just going to do one more real quick. I want to do something that has more than one solution. Okay, so yeah, this is a little uglier, but the x's and the y's don't mix. So here comes another example. So f of xy is x to the third plus y to the third minus 3x squared minus 3y squared minus 9x. Okay, bit ugly. Fx, if you take that first derivative, pretty clean, 3x squared minus 6x minus 9, which factors as 3 times x minus 3 times x plus 1, and you set this equal to 0. So from this, you're going to get x is 3 or x is negative 1. Okay. Now the partial with respect to y is 3y squared minus 6y. That's it. Okay, which also factors, so you're going to have a 3y times y minus 2. You're going to set this equal to 0. Okay, now I'm not going to draw any conclusions. What I want you to do when you do this is to break this into cases. So we're going to do a case 1 and a case 2 when you get multiple solutions. Look at one equation at a time. On the first equation, you have two choices, x equals 3, that's case 1. X equals negative 1, that's case 2. Now, in both of those cases, it must be true that fy is 0. So we know that 3y times y minus 2 has to be 0 in either case. Okay, so in each case, you get y equals 0 or y equals 2. So you get a whole bunch of solution points. You get 3, 0, 3, 2. You get negative 1, 0, and you get negative 1, 2. So see, there's 4 solutions this time. Okay, any questions? And this is a drag because you have to do all these partial derivatives and you have to run the test on all 4 points. So I'm going to come over here and do the second partials now for the second partials test. fxx is going to be 6x minus 6. Okay. fyy is going to be 6y minus 6 also. Now, because the variables don't mix, when you do fxy, you're going to get 0. Okay. I might make a table like this. There's 4 locations, so it's probably best to be sort of organized. So maybe let's do xy. Let's do an fxx. Let's do an fyy. Let's do an fxy. Let's do a d, and let's do a conclusion. Like that. Okay. So let's list all the points. 3, 0, 3, 2, -1, 0, and -1, 2. Okay. So fxx is 6x minus 6. You could think of this as 6 times x minus 1. So x is 2. That'll be 6 times 2, which is 12. fyy is 6 times y minus 6, or if you like, it's 6 times y minus 1. But y is 0, so this I think is going to come out as a -6. fxy is 0 in every case, so I'm just going to go ahead and put that down as 0 all the way. Okay. And maybe it's worth stepping back to remind ourselves what d is here. So I'm going to make a little bit of space since I didn't do that. And remind you that d is fxx fyy minus, run out of space. That's no good. Minus fxy squared. Like that. And I'll squeeze the conclusion in really small. Okay. So fxx fyy, that'll be -12, 12 times -6 minus 0. So I think that's -72. Like that. And when d is negative, remember the second partials test? That's a saddle. Okay, I'll go back to the test real quick. Way back here. If d is less than 0, then f has a saddle at xy. Okay, so going back, we have d negative here. That's a saddle. Now let's do 3, 2. Fxx will be 6 times 3 minus 1. 6 times 2 is 12. Okay. Fyy is 6 times y minus 1. Well, that's just a +6. D is 12 times 6 minus 0 squared. So that's going to be +72. Okay. So the fxx is positive and the d is positive. So going back to the test, that's this case here. Both of them are positive, so that's a local min. And that's our conclusion for the next one. Okay. Next one, -1, 0 is the point. Fxx is 6 times -1 minus 6, which I think is -12. Y is 0, and fyy will be 6 times 0 minus 6, which is -6. We get a +72 again. Okay. So d is positive and fxx is negative over here. So just to remind you, when D is positive and fxx is negative, that's a local max. Okay, almost done. Now at -1, -2, fxx is going to be 6 times -1 minus 6, which again will be a -12. Fyy, okay, y is 2, so 6 times 2 is 12 minus 6 is a positive 6. So once again, d fxx times fyy, that's -12 times 6 minus 0 squared is a -72. Don't have to go another step, that's a saddle. Whenever d is negative, you have a saddle. Okay, so that's your that's how you make the classifications for each critical point. I'm going to pause and wait for questions.
So can we say that here the local mean and local max are the absolute mean and absolute max?
No, you cannot say that, and they rarely will be. You have to remember this is a quadric surface. Sorry, it's a cubic. X to the third goes to infinity when x gets big, right? So when x and y become large, you can expect this to go to infinity. But if they go negative and large, then it will go to negative infinity. So there is no there is no absolute max or absolute min on this surface. And there rarely will be unless you put boundaries around the surface, which we have to cover as well. Any other questions? We will put boundaries and there will be absolute maxes and absolute mins, but not yet.
So the last problem, it is the absolute min.
Yeah, you're right. That one was an absolute min. Only because we're sort of using common sense there. It's quadratic, so it goes up everywhere eventually. But this process with the second partials test is not about classifying absolute maxes or mins. It is only about classifying local maxes or mins. If you're going to do an absolute max or min, you have to have a different tool for arguing, which we'll talk about. Okay?
Okay, thank you.
Right now we're just doing local. But before going on, I want to go ahead and I want to try and graph this. Okay, so in Maple, there's a plot 3D command. And I'll just type this surface in. Again, it was x to the third plus y to the third minus 3x squared minus 3y squared. And then it was minus 9x, like that. And then I can give limits for x and y. So I want x to go from, let's see, I have to have x go from at least -2 because I have a min where x is -1. Sorry, that's a max where x is -1 and a saddle. So I'm going to go back to -2 on x, and then as high as the biggest x, which is the 3. I have 2 critical points where x is 3, so I'm going to have x go up to 4. Now my y points, the critical points have y equal to either to 0 or to 2. So I'm going to have y go from -1 to 3. And that should capture all the features we're looking for. Yeah, that's a better picture. Okay, so I think you can see, I'm going to point to this. There's a saddle right down here. And there's a saddle up here. The local max is up above. And I think the local min will be down here. Okay, so I'm just going to copy this. Can I do that? Yeah, I don't know how to capture that over to my laptop. That would take a little bit of thought. So I'll put that in after class. I'll just leave that up. How are we doing? 8:31. Yeah, so let's go over to the notes. I think that's all we're going to squeeze in today. There's still more to do on this lesson. So that's about it for 14.7 right now. I'm going to pause the video. All right, so we're looking for absolute maxes max and min over closed and bounded regions. And without making a big fuss, the theorem just says that if f, and I won't say how many variables it is a function of, but if f is continuous, over a closed and bounded domain, then it has an absolute max and an absolute min in this domain. Okay. If the function is not continuous, then there's no guarantee. If the function goes to infinity, then it can't be defined on a closed domain. To go to infinity is to automatically be over an open region, because the infinity doesn't have a boundary, and closed regions must have boundaries. And that's kind of the definition of a closed region, that it includes its boundary. So let's put that down here. Closed means the region includes its boundary. Oops. Okay, bounded. There's a lot of ways you could say this. You could just say you could draw a circle around the region. If you want to be more precise, you'd say you can enclose the region in a circle, or in parentheses, or a sphere if it's three-dimensional, or hypersphere if it's four-dimensional or higher. Okay, so just depends on the dimension what we're talking about. These are all effectively spheres in their appropriate dimension. Okay, so just on closed and bounded regions. So this kind of boils down to just a step-by-step process now. So let's go ahead and put a step-by-step in, finding absolute max and min points for f of x, y, or let's just say f, over closed / bounded region D. Okay, so first step is you'd have to find the critical points inside D, in the interior of D. So that'll be step one. Find critical points in the interior of D. And that's where points where all partial derivatives are 0. I'll say where all first partials are 0. Okay. Any questions? So you got to find those critical points inside D. Now, secondly, you're going to have to find critical points on the boundary of D. This is harder. And it requires that you parameterize the boundary. Okay, so parameterize the boundary of D. Then look for critical points on the boundary. Okay. Third, you have to find points on the boundary where this where D is not smooth. Okay, so find all points where the boundary of D is not smooth. Okay. Fourth, evaluate F at each of the points above. Okay. Wherever F is largest is an absolute max. Okay. Wherever F is smallest is an absolute min. And you're done. That's a lot of work. It involves solving systems of equations because you're going to have multiple partial derivatives. Then you have to set them all equal to 0. So each one of those is an equation that has to be solved simultaneously as a system. So that's not great. Okay, I just want to kind of maybe draw a little diagram here. So maybe just a picture down here. So here's my region. Okay, so this is D. Okay, this is the boundary of D. And these are points where the boundary is not smooth. Yeah, they're like cusps, but they're cusps of a boundary. Things tend to break down on cusps, so you have to check those as special cases. All right, so for our first example, we want to let f of xy be x squared plus y squared minus 2x. Over D, which is just a triangle. It's really the region inside the triangle and the boundary with vertices 2, 0, 0, 2.
Sir, we have a frozen screen.
And, okay, one moment. 0, negative 2. All right. Okay, so we're going to let f of xy be x squared plus y squared minus 2x over D, which is a triangle with vertices 2, 0, 0, 2, and 0, negative 2. And that's just the boundary. Actually, the entire region inside is part of that as well. Okay. All right, so we're going to go through the steps that we outlined up above. The first thing was to find the critical points in the interior where the partial derivatives are 0. So the first partial, this is step 1. First partial is 2x minus 2. Set it equal to 0. And of course, x is 1 there. Okay, any questions? Second partial derivative is fy, which is just going to be 2y. Okay. Setting this equal to 0, of course, means that y is 0. So we only get one critical point, 1, 0. I should say that's the only critical point in the interior. The interior of D. Okay, so maybe we should draw this thing. I'm just a little nervous. Right, okay, so just a real quick sketch here. So here's 2, 0. Up here is 0, 2. And down below is 0, negative 2. And maybe I'll do that in green. So we get our triangle. And I think I'll shade it just because. That's kind of small. That's okay. Okay, any questions about this region? And we got a critical point at 1, 0, so that's right in the middle here, right there. 1, 0, critical point. Okay, any questions? We want to parameterize the boundaries. So I think I'm going to give them names. So this boundary on the left, I'm going to call B1 for boundary 1. And then 2 on the right, on top, we'll call B2. And down below, B3. We have to parameterize those. Okay. So this is step 2, I believe. I'm going to go back up and double check this. Parameterize the boundaries, then look for critical points on the boundary. So if the boundary is made up of multiple segments, you have to do each segment. Okay. So on B1, so on B1, we know that x is 0. So the parameterization is just y is equal to y. And so f of x, y would be really f of 0, y, which is y squared. Okay. The derivative now will be a regular derivative. So the derivative with respect to y of f of 0, y will be 2y. Set it equal to 0, and that means y is 0. So we have one critical point, 0, 0. On B1, so I'll put that in as a green point as well. Right on the edge. Got to check that. That could be a max or a min, an absolute max or an absolute min. Somehow I doubt it, but I don't know why. Okay, any questions about that first boundary? You guys all seeing this okay? I'll take that as a yes. All right, so now that's just one of the 3 boundaries. Let's look at boundary B2. So on B2, let's see if we can think. Slope is -1, the y-intercept is 2. So this is y equals 2 minus x. Okay, so f of xy is f of x comma 2 minus x, like that. That's going to be a little more work. So let's see, what's f of xy again? Way up there. Okay, so I don't know if I can squeeze this in, but I'm going to try. It's x squared minus plus y squared, which is 2 minus x squared, and then minus 2x.
Sir, quick question.
Yes.
Is y supposed to be equal to x minus 2? Oh, sorry. No, you're talking about B2. Never mind.
Yeah.
All right.
Yeah, I'll catch up to you in a sec. Okay, so let's see. This is equal to x squared plus, and this is going to be 2x squared. There's going to be a minus 4x minus 2x. I think it's minus 6x. And then plus 4. Now I'm just going to double check my work there. X squared plus x squared is 2x squared. we get a negative 4x minus a 2x, and then plus 4. I think that's good. Any questions? And this is what we have to take a derivative of, so we'll go with that. Derivative with respect to x of f of x 2 minus x is going to be 4x minus 6. You set that equal to 0. So x is going to be what? 6 over 4, so that's 3 halves. Y is 2 minus x, so y would be 2 minus 3 halves, which I guess is 1 half. Okay, so that means you've got the point 3 halves, 1 half, like that. Isn't this horrible? 3 halves, 1 half. That would be right on the boundary. So I'm going to try and rejigger my picture a little bit. Three halves, 1 half is going to be right here, I think. So that guy is 3 halves, 1 half. Okay, any questions? That's a critical point. You got to check it. It's a possibility for a max or a min. All right. Now we have one more boundary, B3. Hopefully we won't get too much here. So we'll see. Oops. Okay, so on B3, y is, as was suggested, I think it's x minus 2. So that's got a slope of 1 and a y-intercept of negative 2. So it's x minus 2. And so f of xy would be f of x and y is x minus 2. Like that. Okay, and let's see here. That should be x squared plus x minus 2 squared, and then minus 2x. I think that's exactly the same as before. I think that you're going to get x squared minus 6x plus 4. Okay, and I'm going to jump through these hoops here. So the derivative with respect to x of f of x comma x minus 2, we've already done, that's 4x minus 6. So that means x is 3 halves. Now y is different though. Y is x minus 2. So this will be 3 halves minus 2, which will be negative a half this time. So this time your point is 3 halves and negative a half. So there's a little symmetry to that compared to the last one. And I'm just going to kind of shrink this down a little bit and squeeze it in. I'm just going to go straight down below the last one, like here, and reference it. All right, any questions? Isn't that horrible? So those are critical points on the boundary. That's step 2. Okay, there's also step 3, as you know. So I'm going to go back to that. I'll come back down. But step 3 is to find all points where the boundary is not smooth. So here we go. You can see those are the corners of the boundaries. So just real quick, we're on step 3 now. So the boundary is not smooth. At the corners. So those were 2, 0, 0, 2, and 0, -2. Okay, that was easy. And step 4. Now there's no second partials test. We're not looking for local mins and local maxes. You can do those any way you want. I mean, technically, any of these critical points we've listed could be local mins and local maxes. The best way to do that, I mean, you could beat this thing to death. You could study it and study it and study it. You could do a second derivative test on just the boundaries to find out where it's concave up and concave down. And these are just ordinary derivatives on the boundaries because you've parameterized in terms of one variable, x, or in one case we parameterized in terms of y. So because those are parameterized in terms of one variable, you could do normal derivatives and use normal calculus to look for maxes and mins on the boundaries. And they could be local maxes and local mins. And you could do a first derivative test or a second derivative test on the boundaries as you did in Math 180. Okay, so there's nothing really new when you study the boundaries. Those are one-dimensional. But regardless, we're looking for absolute maxes and absolute mins. The only thing that's required of us is to make a table and put everything in it. And I do not like doing this. Okay, here we go. I'm going to get the list first. So the first point was 1, 0, and then the 3/2 plus or minus a half. Got it. So there was 1, 0. There was 3/2, 1/2. There was 3/2, -1/2. There was, well, this took a lot longer. Oh, did I miss one? I missed 0, 0, darn it. That's okay, doesn't matter what order you do it in, 0, 0. That's everything. Wow, except for the corners. So then we got to put those into 2, 0, 0, 2, and 0, -2. Like that. Isn't that delightful? Now, Bilal says, what would the method be for finding where it's not smooth if we weren't given something that was obvious? I would say, Bilal, in general, you're looking for where 2 curves meet. How about that? It won't always be a rectangle. Okay. Now, Javier, I see things are frozen again. I gotcha. I'm going to restart. Okay, so we need to evaluate the function at all of the points that we found to this point. So these are the points. We have to evaluate the function at all of these points. And as we say, wherever f is biggest, you've got an absolute max. Wherever f is smallest, you've got an absolute min. Okay. I see a question from Brandon. Brandon, I'm going to get to you in a second. I just want to finish this problem real quick. Okay, so I have to evaluate the function. Now remember f of xy, let's get that formula down. This was x squared plus y squared minus 2x. All right, and being a little lazy, I'm going to move my share over to Maple real quick. Pardon me one moment. Okay, now I think you're all looking at Maple. Let's go ahead and do this real quick. We've got f as a map from points x, y, outputting to the function. Oops, I did not mean to do that. I meant to do that. Outputting to x squared plus y squared, and then minus 2x. So that's how you define a function in Maple. It's a little weird. And then I'm just going to evaluate at all these points. So f of 1, 0 is going to be -1. F at 3 halves, 1/2 is -1/2. F at 3 halves, -1/2 is -1/2 also. We know what f of 0, 0 is. F of 2, 0. I guess most of this we could have done in our head. F of 0, 2. F of 0, oops, 0, -2. Okay, so I'm just going to fill those into the table that we made and move my share back to my iPad. Okay, so at 1, 0, we got -1. 3 halves, 1/2, -1/2. And the next one's also -1/2. At 0, 0, we got 0. 2, 0 is also 0. 0, 2, and 0, -2 were both 4. So we have absolute maxes at these locations. Oops. It's a tie. You can have 2 locations that are absolute maxes. Okay. And then the absolute min is at 1, 0, right in the inside. Okay. All right, so there's that. Now I want to go ahead and try and graph this for you. So I'll paste that over if I can be clever about it. I think I'll pause the recording right now. Okay, so now we can just annotate this a little bit. Right here is the point, that's 0 on x and 2 on y. So that's 0, 2, 4. Z-coordinate's 4 there. Okay. Back here is 0, -2, 4 there. The min, absolute min, is down in the bottom here. So that's where, what was that? That's 1, 0, -1. And you can see there's a local max. I'm going to erase this in a second, but this guy right here is a local max. And the two absolute maxes occurred not at critical points, but on corners of the boundaries. These are the places where the boundary is not smooth. And the local max occurs at a corner. The only thing that's not at a corner is the absolute min, which was at a critical point in the interior. Okay, and I think that's all we're going to do with that section of the book. I'm going to pause the recording here. And see if I can address